Last week I made a video about cats versus Zero for seasoned Scala developers, and in that video I promised to make another version of it for beginners. Now, in order to do that, you need to really understand functional programming, and so this video is also going to serve as sort of a crash course. In fact, we'll cover pretty much everything you need to know about functional programming. Now that I'm thinking about it, I might as well call this video like this. Yeah, I think it sounds good. Anyway, let's roll the intro. Hey, Vlad here from devinside.com. Welcome to another video. Now, this is mostly a Scala channel. However, if you stumble on this video for any other reason, don't worry, most things are applicable to any other language. And since you're new to Scala, allow me to welcome you to the Scala community. Welcome. Scala was one of the first, and it might actually be the only programming language out there that successfully managed to combine the object-oriented and functional programming worlds in a seamless way. Now, nothing is perfect in this life. Everything has trade-offs. One of the challenges that this, even though successful mix poses, is the fact that now you as a programmer are left with too many choices for building software. And so, since the beginning, the always evolving Scala community was searching for the best way to do it. Now, since you're new to Scala, there will be a lot of by-the-ways in this video, and here's the first one. Even though Scala is a general-purpose programming language, it found its niche in A, wherever Java found its niche, which is in the backend of web applications, which is also what this video is concerned about, and B, in the world of big data, which is not what this video is concerned about since I'm not a data engineer. If you're serious about diving in the world of Scala, rather sooner than later you will discover the fact that we have a lot of tech stacks to choose from. Some of them lean towards object-oriented programming, some of them lean towards functional programming, and some of them are somewhere in the middle. Now, backend applications tend to grow over time, and functional programming offers solutions for maintaining large pieces of software, and so over time the Scala community leaned towards pure functional programming. We will talk about purity later in the video, but the point I'm trying to make is that even within this functional niche, you still have choices. So one of the goals for this video is to help you choose, and the way we're going to go about this is by explaining the appeal of functional programming in a non-hand-wavy way. Let's begin. Right after the message from our sponsors, which is you, the people who support me on Patreon. Without you, I wouldn't be able to pay for my video editor who allows me to spend more of my time to hang out with you during live streams or answer your questions on Discord. There's many of you and only one of me, so every dollar counts because eventually it adds up. Special thanks to Fred Albu and Johan for being my highest tier patrons. Thank you. Now let's talk about functional programming. First and foremost, I already made a video about programming paradigms, so you might want to check it out. Also, I made a Scala crash course, which is 3.5 hours long, so you might want to check it out as well. By the way, guys, the theme for this video is to be sort of like a crash course, so we're going to move pretty fast, okay? This video, even though it is for beginners, it's not for absolute beginners. Like, I hope that you have like maybe a year of experience in some other language. Now, what is functional programming? Well, functional programming, same as any other paradigm, is a set of constraints, aka a discipline that we, the programmers, follow to maintain potentially large pieces of software. Now, one important thing to keep in mind is that this discipline is imposed on you, the programmer. Now, programming languages, type systems, tasks, and other tools are useful, but at the end of the day, they're not bulletproof. And if they were, we'd have Skynet, and you wouldn't have a job. Now, every discipline has a cost, and functional programming is not excluded from the statement. It's only worth the price, and thus valuable, in large, always changing applications. In fact, this is what software is all about, right? It's about change. Software is easier to change than hardware. Now, what is the value of functional programming, or in other words, why would we constrain ourselves to follow this discipline? Simply put, as a programmer, we have many things to worry about, and functional programming removes some of those worries. It reduces bugs and prevents regressions, thus giving us more confidence when we want to change our applications, which is something that happens all the time. But remember, it's not bulletproof. Now, what is this constraint though? What is it exactly that we need to give up? Now, the answer to this question is assignment, but it doesn't really help you, does it? This is also the reason why usually when FP is presented, you're just bombarded with buzzwords like immutability and the fact that it somehow helps with concurrency, and there's talk about recursion and lambdas and referential transparency. As I said, many buzzwords instead of giving it to you straight. What I have for you today is a repository with 32 commits, and we're going to go through all of them. I used to do all of this stuff live, but it turns out that typing takes a lot of time, and this video would be like 3 hours long. So we're going to simply run through 32 commits over here, and this repository is also going to be on GitHub. And if this video turns out to be too long, I'm going to cut it into two. The goal is to focus on the question that most FP beginners have, which is how to do an immutable print line. And somewhere along the way, we're going to define functional programming very precisely without any hand waving. Let's start going through this repo. So Git allows you to only go backwards because the pointers point backwards, which is why I tagged everything like this. So you can check out any tag you like, and I'm also going to be pushing these tags. Okay, so I have made videos about ZSH and OhmyZSH, and OhmyZSH comes with a Git plugin which comes with a bunch of aliases. So today we're going to use a bunch of Git aliases. Okay, so I'm going to show you a couple. So GCO is Git checkout, GSH is Git show, and git show -s is like git show, you know, short. And yeah, this is pretty much all we're going to need. So what I'm going to do is I'm going to check out the v1, right? And I'm also going to do gpristine. Gpristine is pretty much going to remove a bunch of stuff that is like laying around. Hold on, gpristine, like this. Okay, so it's basically git reset hard and also git clean with a bunch of flags. Okay, so as you can see, we're now, you know, if I do log, it, you know, the hat is over here. So this is the initial commit. So I'm going to open it with Visual Studio Code, and I'm going to show you what we have. While it's loading, we're also going to import the build project. I'm going to give you like a couple of pointers about Scala, but ultimately this video is not necessarily about Scala. It's not about like the build tools and anything like this, but you know, you're a beginner, so I'll try to give you like a little bit of something so that you're not completely lost. What we have over here is the terminal, and over here is my file tree. And as you can see, I prepared two files. One is called mutability and the other one is called immutability. So what we're going to do is we're going to run with a typical banking account example. I have two versions. One is a mutable version, another one is an immutable one. And I'm pretty much going to use them just to sort of explain to you, you know, the Scala syntax and stuff. Okay, in fact, maybe I should do this, and I'm going to throw like the immutable over here and go like this. And for now, we're going to disable the console like this. So once the build tool finishes compiling, we're also going to have buttons over here for running and debugging, but we're not interested in that at all. We're using Scala 3, which has Python-based indentation syntax. So for example, this is a class, and this here is the body of the class. It's indented by 2 spaces, and there's a colon over here. The syntax came in Scala 3. Okay, so this is pretty much a main method, and this program pretty much creates a bank account, mutates it a little bit. In fact, we should probably run it. So I'm going to launch SBT, which is Scala's build tool. So we're going to, come on, there you go, clean the project, and we're going to run it. It's going to compile. It's just only 2 files, so the compilation is going to take just a couple of seconds. So we're going to run the mutable version, and it presents 0/2015. So now we're going to run the immutable version. It does the same thing. Okay, so let's go through the scope. So this is like the main method. We're printing out a bunch of hyphens. Then we have a class called mutable bank account. This is how constructors are done in Scala. So this field initial balance is of type integer. It is not going to be accessible from the outside. So in Scala, this is technically a private val. Vals are constants. Okay, so everything that is here is 2 things. One is this is the constructor body, and also this is all the members of the class, which is, you know, functions, you know, methods, right, and other fields. Okay, we have a private variable, right, which means a mutable reference to an integer, and in the beginning, in the constructor, is going to be initialized with the initial balance. Okay, this is pretty much a getter for the balance, right? So this is just a definition. This is a method without any parameter list, and its default value is going to be current balance, but this is a method, right? And because this variable is mutable, whenever this changes, the getter will give another value. We have deposit and we have withdraw. That pretty much, you know, we give it the amount. We're either adding the amount to the existing current balance, or we're withdrawing, we're removing it. We're not worried about arrow handling or type safety or anything like this here, okay? Over here, we're creating our first mutable bank account by giving it the initial balance of 0, then we're printing it out, which is why we saw the 0. Then we're depositing 20, let's say, dollars, and then we're printing it out again, printing out the balance, right, by using this getter, right, because it has access to the mutable variable. Every time the println is going to be different, so we're printing it out. and then we're withdrawing $5, and so we're left with 15, right? So over here we had 0, 20, 15. Let's have a little bit more space like this, okay? The immutable version works pretty much the same way, like most things look exactly the same. It's a final class. Now, this is not a private val. This is a val, which means it is accessible from the outside. So we can do immutable account dot balance. Over here, we didn't want to do this because we only wanted the getter to be visible, but not the setter, right? Only the methods inside of this class will be able to modify this current balance, but on the other side, you're still going to be able to see it. Immutability doesn't have any issues with it, right? So we can have this balance because it will never change, right? So over here, we're instantiating the immutable bank account with a 0, and it will be forever 0. So how do we deposit or withdraw things? Well, instead of returning a unit, which is something like void in Java, we're going to, every time we're going to change something, we're actually going to create a new bank account. So over here, as you can see, deposit creates a new bank account, takes the balance of this account, adds the amount that we're passing in, withdraw has a minus over here, right? And so anytime we deposit, we're actually creating a completely different bank account. Okay, over here, withdraw, completely different bank account. So we kind of have like versions of the bank accounts if we stick around using those vals. Okay, I think a debug point sneaked in somehow. Now, this point is already very important because immutability already seems more sensible, right? You kind of have this intuition that immutability is somehow better. You know, there's no mutable state, so it's probably good. If there's no mutable state, then there also cannot be any shared mutable state. So this is how concurrency is solved. You know, usually around this stage, people also talk about referential transparency, but this sounds like a very fancy word. So don't worry about any of that. We're going to discover all of these things step by step, and there will be no stone left unturned, right? So you will know exactly what referential transparency is, and you will know exactly why mutability makes more sense. Not every commit is going to be very big. Okay, so let me first see. So when I do this short thing, I'm only seeing the description. Okay, just to remind myself what it is going to be about, and now we're actually going to see what happened there. Okay. So as you can see, this is the only thing that happened there, and I'm actually going to check it out, okay? In fact, I think what I should do is I should do this over here, okay? So I'm going to open the console, and I believe I can do something like over here, split terminal. I'm going to use the SH, okay? And I know that I'm covering like some parts of this, but it's not that much of an importance of what is written like in the bottom right corner. So what I'm going to do is I'm going to check out v2. So as you can see, this is the only thing that changed, and I simply made this change because I'm kind of like walking you through the whole thing, just to point out that there's always something returned because we're in Scala, and Scala is an expression-oriented language. So everything is an expression, which means everything has a value, and because it's a mix of functional programming and object-oriented worlds, every value is also an object. There are some optimizations when it comes to primitive types, but none of them matter today. This is just a fancy syntax for when we are not interested in specifying the name for our variable because we're not going to reference it at all, right? But it will become important much later in the video why I'm pointing it out like this. Let's not dwell on this. Let's just move on. So version 3 is no intermediate state, okay? So over here, we have an immutable bank account, but we kind of go through like intermediate states. First, we create like the second bank account, then we create the third bank account, but at the end of the day, we just wanted to create the third bank account. And we kind of do like the same thing over here. We're not creating intermediate states, but we're going through intermediate steps, okay? And so all that this thing is showing is that you could, you know, because one of the things about functional programming is that usually people say, oh, you know, it's like less code, it's like, you know, everything is shorter, it's nicer. This is not what this is about. I want to show you that you can do this both with the mutable version and the immutable version as well. Okay, basically over here, we're not using any intermediate states. So the immutable version kind of makes sense because this is also called fluent interfaces, right? Because this line gives an immutable bank account. On that immutable bank account, you can call deposit, right? But what does deposit return? Well, it returns an immutable bank account. So on that immutable bank account, you can call another method called withdraw. And in the end of the day, you're getting your third bank account, but kind of have only one val, and therefore we only, you know, it kind of feels like we only had only one bank account. Okay. Also, usually it's one of the beginners concerned about functional programming that there's like some copying taking place, but most of these problems in functional programming are actually solved by a thing called persistent data structures. But I'm going to talk about them today. We're also going to talk about recursion, which is a common thing that functional programming tutorials talk about, because ultimately functional programming is not all about recursion. And also, especially like in real world application, even if your entire application is written in a purely functional style, you might not have even a single recursive method, because all of these things are like abstracted away. They're hidden behind, utility methods. So the immutable one kind of works the same way, right? So in Scala, we can have, vals inside of vals. We can have even classes inside of vals. Scala is a very regular language. There aren't that many exceptions in terms of like syntax. Okay, so we're creating a val bank account, but there's a teeny tiny val inside of it called result. Usually it's called result or some sort of like accumulation. So this is essentially a bank account. Then we deposit, we withdraw, and then at the end of the day, we return it. Okay, so this is also one of those things that usually when you start out with Scala, people tell you, don't use var. Var is like mutable stuff. But it turns out that mutable stuff has actually nothing to do with the vars, because even though this is a val, right, the mutable state is inside of this thing. Like typical example would be an array. You can have, val x equals, array of 1, 2, 3. The array is mutable, even though the reference will always point to this array. It's just that the question is, what is this array? The array can mutate. It can change in place. Again, the point of this whole exercise so far was to show you that it's not all about like, the fact that the immutable code is like shorter and more pleasant to read. It is a point, but it's not like, it's not what this is about. Okay. Let's go and see what's up with the next one. So the version 4 is tap. So one of the things that you learn about is lambdas. Lambdas are just a syntax for function literals. Okay, so the same way as you can have a literal for a number, like 1, 2, 3, you can have a literal for a function. Now in Scala, this literal is just a syntactic sugar for an anonymous class that is going to be instantiated, right? So it's going to turn into an object at runtime. And there's a lot of like syntactic sugar around it. So what I want to show you is that you can even get rid of this val result, so that syntactically these two things, even though one is mutable and the other one is immutable, can get even closer. Okay, so I'm going to check it out. So this is v4. These two functions are present in the Scala standard library. In fact, the next commit throws them out and uses an import. Okay, but let me explain to you the syntax first. First of all, like this is a feature in Scala 3. It is also possible to do this in Scala 2. It's just that the syntax would be slightly different. And this is an extension method. It's also present in other languages like C#, for example. And this extension method extends all kinds of types. We're giving this type a name, A, which means you can stick any type into it, but in this scope, it is going to be known as A, right? And so you're going to be able to call a function called pipe or a function called tap, right? This one on that thing that you're calling, right? So you're going to be, imagine you have something and you can do dot pipe or dot tap, okay? This is what the syntax allows you to do. Pipe is a funny thing. Essentially, maybe I should give you an example. So imagine that you have like two functions, f and g, okay? And then, g takes an a and f takes whatever, whatever comes out of g. And so this is how you would write this code, right? So you give a to g and then whatever comes out, you give it to f. This code will allow you to do something like g of a, right? Take the result, pipe the result into f, okay? Or you can even go take the A, pipe it into G, and then pipe it into F. Okay, so this is what this thing would allow you to do. Okay, so as you can see, it is a higher order function. Higher order functions either take other functions as parameters, or they produce functions as their result, or both. And at the end, it returns a B. Okay, so B is over here, right? A little bit of generics. Okay, so somehow we go from A to B just by calling the function. Okay, the implementation is trivial. Now, tap is actually what we're interested in so far, right? Because I brought in pipe simply because it's, usually they are presented together, but we're going to use pipe only a little bit later in the video, okay? Tap is actually very interesting because even though it looks exactly the same, at the end of the day, it throws out the result of B, right? And it just gives you that thing that you called it on, right? So for example, over here, if this was like a tap G, right? Whatever G returns, which is over here, would be thrown out, and then A would be returned, right? So this pipe will still be called on the A. And this is done exactly for mutable code. So if you look at the bottom, we're creating the multiple bank account, and we tap into it. This is a fancy syntax for, okay, bank account comes in, right? And now we're taking the bank account and we call deposit on it, right? Now the result of deposit is unit, right? But look at this code. We're throwing out this unit. We don't care about this unit. We return that thing that we call it on, right? Which is this mutable bank account, okay? So over here, this tap is still called on the bank account, okay? So this whole thing, at the end of the day, does exactly what I was doing before, but there's no need for this val. So this argument about immutable code, like, you know, it's less code, it's not that valid. Like most of the times, yeah, you can write very concise code. However, again, this is not what this is really about, okay? I'm pretty sure that the next commit, which is v5, is going to throw it out and just do an import to scala.util.chaining, because these two methods are so popular, so common that they are, you know, part of the standard library, okay? And by the way, from time to time, I should actually run the code. So what we can do over here is we can do, you know, run main and then dev inside you, and let's run the mutable version. As you can see, the result is now only 15. What is the next one? Simple mutability challenges. Interesting. So I actually want to see what I did there before I present it to you. So there will be 2 commits in this entire thing. There are like the very crucial key points. You really need to make sure that you understand them, because otherwise everything else is going to be very hard to understand. Let me talk a little bit before I present this to you. So the next commit defines functional programming. It presents a model for understanding how procedures, which are methods or functions, are applied to arguments. This model is called the substitution model for applying procedures, right? For procedure application. So the substitution model for procedure application. Now, this model is not how the compiler or the interpreter interprets or compiles your programs. This is a model for you to think about your programs and to have certain guarantees. This model should be very attractive to you, because this is the simplest model of how to think about programs or pretty much any other scientific or mathematical things. In fact, this model is being, you know, was presented to you in high school, right? So whenever, you know, your teacher, I always use this example, whenever your teacher writes on the whiteboard, you know, x equals 5, then no matter what happens, no matter at what time you refer to x, everything else on the board will still see x as 5. X will never change, right? So again, like immutability kind of like sneaks in, right? But we're going to define it more precisely than just saying, oh, okay, it's never going to change. Let me check it out. Was it 5 or 6? Okay, we're already at 5. Okay, 6. Okay, so this is how functional programming is defined. Imagine you have this code, and I'm going to comment out. all of this. Okay, so this is how this program is running. In fact, we don't need the other version for now. This is all that this program is doing, right? It prints out 1 and 1, which is a tuple, okay? So now imagine for a second that you have a val and you don't know what is on the right-hand side of this val, okay? Like this. Okay, by the way, this code compiles because Scala allows not only alphanumeric variable names. So there's actually a definition called question mark, and all it does is it throws a non-implemented error. So we can jump in there and you're going to see that it just throws a non-implemented error. Okay, so this is done for like prototyping code. Imagine that you don't know what this is, which means that you don't know the type of this thing. Okay, now imagine that you wanted to create a tuple, which is a data structure without any special name, right? You can retrieve these values by calling, _1 and _2, okay, later if you wanted to, okay? This is a tuple 2, which is a heterogeneous collection. It can hold 2 things of potentially different types. In this case, it's the same type, okay? So you're taking this A, sticking it in there twice, okay? So now you have a tuple of A's, which is why I called it TA. And so we're printing it out, and then, when there was 1, you actually saw the tuple. So here's the question. When do these 2 programs behave exactly the same? Now, what is the difference between these 2 programs? The only difference is that over here, when we're constructing the tuple, we are not referring to this expression, but instead we're referring to its value. Okay? Remember, the model is called the substitution model. So we're substituting the expression by its value. This is also called a referential transparency, right? So this expression is referentially transparent if these programs behave the same, okay? And for simple values like 1 or an immutable bank account, these programs will always be the same. However, you need to know what you're dealing with, right? In a mutable program, you need to know what you're dealing with, right? If this is an array, you don't know. If this is a mutable bank account, you don't know. And here's an example, right? So here we're introducing side effects that happen on the side, okay? So all of these 4 programs are kind of the same, right? They all start with something, then a tuple is being created. In the first version of the program, the tuple is being created by referring to the expression. And in the second version is by literally substituting the expression with everything that is following the equal sign over here. Okay, I'm going to remove the console so that you see the whole thing. Okay, so literally like this copied, pasted once, pasted twice. And a bit later, we're going to have a version of this with a mutable bank account. Okay, but for now, it's just print lines. So if we run this program now, you're going to see that it actually does not behave the same. What does this mean, right? So one program does this, the other program does this. This is different behavior. What does this mean? Well, it means 2 things. First of all, this expression, this one, well, technically this one, right? But you know what I mean, right? This expression is not referentially transparent. So referential transparency is a property of an expression. And it means that when an expression is referentially transparent, it means that the time when you refer to this expression doesn't matter, right? Remember, like if x equals 5, no matter if you call it in 100 years, x is still going to be 5. Remember, it's like this immutability thing, right? Now, the substitution model is a property of the entire application, right? So now, because until we have this program, excluding these print lines are just for you to help you understand. But if these print lines were not around, right? Like these 2 programs, right? Like again, like forget about these print lines, like real quick. These 2 programs, this entire program was not breaking the substitution model for procedure application, right? So it gave you certain guarantees. It allowed you to treat these expressions simply as aliases, right? But once we introduced this, we broke the substitution model for procedure application. And now if this was a huge application, we would lose this ability to reason about our programs in terms of this very simple model. And this is the definition of functional programming. A programming is written in a functional style. It's a purely functional programming if you did not break the substitution model for procedure application. Okay, which means every expression is referentially transparent, which usually means every expression is immutable. There are some caveats. We'll get into that. Okay, so let's get into the next one. And the next one, I'm sure, is going to be, by the way, grhh is git reset hard, right? Which means that let's throw out all the changes. Okay, so let's do git checkout v7, and I'm pretty sure that in v7 we're working with a mutable bank account. Okay, now it's exactly the same thing, right? So we're creating something, right? So there's something on the right-hand side of the equal sign, right? We're not doing that yet, okay? We're putting like 2 of these things into a tuple, then we're doing a print line. Now, one important thing to notice is that just because you have mutability, or just because you're breaking the substitution model for procedure application, sometimes your program will behave just fine, right? So as you can see, the bank accounts are not affected. Obviously, we're seeing these print lines, but at least the bank accounts are not affected. And you can say, well, who cares about the print lines, right? But sometimes it is, right? And this is the problem, right? So because sometimes with mutability, you will sometimes have bugs that are very hard to reproduce, because if you wanted to reproduce them, you will need to talk to your users and you would need to say, okay, well, what did you do? And then it will say, okay, well, first I did this, and then I did that, and then did that. And then you need to go to your program and you need to replicate exactly the same thing, okay? So here's an example, right? So if we do this, right, then all of a sudden, not only print lines change, right? So this affected this bank account, and the second bank account was not affected. Okay, so second bank account is still a 1. Okay, so now these programs don't behave the same. The substitution model is broken. And why is that? Because this expression cannot simply be treated as an alias to some value. It is an alias only within some environment. In fact, the model that you need to apply here to think about your programs is called the environment model for procedure application. In fact, these are just like the official computer science term for object orientation, which is the environment model for procedure application, and functional programming, which is the substitution model for procedure application. And I have very, very old videos about this, and most of the stuff comes from a wonderful book called SICP, which stands for Structure and Interpretation of Computer Programs, and I have a review somewhere on my channel. I'm sure you can find it. Let me throw this out and let me demonstrate the immutable version. Okay, so let's switch to running the immutable version. So as you can see, it's the same thing, right? So ignore the print lines, right? So the print lines are still messing up with the substitution model, and the rest of the video is going to explain how to solve this problem. Okay, so look at this. If we enable these things, the bank accounts are still not going to be affected, right? Why? Because this simply creates another bank account, and we're throwing it out. Remember this thing, right? So this equal sign, this underscore here is another bank account. Right? So if I were to give it some name, my ID will actually tell me, well, this is actually another mutable bank account. But we're not doing anything with it, right? It doesn't participate in the rest of the program, which means that, none of the stuff is affected, right? Like this. Okay, so either like this or like that, everything is fine. Okay, and one important thing is that, let me actually switch to the mutable version again. It is very hard to reason about this. If we go to mutability, all right, and we do this withdraw, well, actually, no. Look at this. So there's like 1, 1, 1, 1, okay? So over here, this toString, which is something that I added, which, just prints out the bank account. If we change it to a val, it behaves the same. If we change it to a var, it behaves the same. Well, it cannot be a var, okay? If we change it to a lazy val, it behaves the same, okay? Now, let me change it back to def, okay? So this is a very interesting point, right? Because depending on what your program is doing, you might or might not create bugs, right? So you have already broken the substitution model, but so far it doesn't bother you, but sometimes it does, right? So if we have this, okay, see, we have like 0, 0, 1, 1, right? So it's already not the same. But now also, if you go over here and do a val instead of def, then stuff change. So it's very, very, very hard to reason about programs like this, okay? Because the substitution model is broken, right? But only because it's broken doesn't mean that you easily see it, right? All right. So next one. Let's show V8. I believe over here, I just wanted to show you the pipe because I introduced the pipe before. Okay, and it is over here. Okay, so this is going to be very, no, it's actually, there's actually another reason why I'm introducing the pipe, because later we're going to learn about map and it's going to be very, very similar. Okay, so another way like to write this would be like this, right? So look over here, right? So instead of just like doing like e dot withdraw, we can do e pipe, and then like this is going to be this is the same as, okay, like it's still the same e, right? So this is like a little bit of a silly code, but later it's gonna make sense. Okay, like this. All right, let's have a look at the next one. This one is very, very important. Okay, so remember, when you still need to solve the print line somehow. And by the way, guys, don't forget to hit the like button so that more people stumble on this video. Really helps out the channel. All right. If I'm correct, then this is another one of those commits that is very, very important. Why are we having this problem with the print lines? And usually the answer is because they happen too early, right? So they already happen, and therefore, it's very hard to apply the substitution model for things that already ran, they already happened, which is why most like very, very pure functional programming languages, and we're going to talk about purity in just a second, most of them tend to be lazy. They have on-demand evaluation semantics, which means that this val, this code that is inside of these curly braces is only going to be run when we're actually going to use the E, okay? It has different trade-offs, but like this is what it is. Like most programming languages allow assignment, allow mutability, and therefore most of them are so-called eagerly evaluated programming languages, or strictly evaluated programming language, which means that if there's a val, it's going to run immediately, even if you don't use it. Now the question is like, how do we solve this print line? Well, we need to delay it somehow. right? Artificially delayed. And the way to delay it is basically to say, okay, well, we know that when this code runs, we're going to side effect, right? So let's not run this code, but let's remember how to run this code. Okay, usually when functional programming is explained, the term description is used. Okay, so let's convert this into a description of whatever happens inside of these curly braces. Okay, and the way you do this is by saying, okay, well, E is just going to be a function, that, it's not going to have any arguments, right? But when we're going to call it, then, then we're going to do the println. And the trick is that we're never going to call it. Okay, instead, what we're going to do is we're going to, so this basically delays this expression, right? So we're going to delay all of the expressions. Then we're going to figure out how to combine all of the expressions into one. And so your program, no matter how big, and I know it's very hard to imagine like a back-end application, which was thousands and thousands of lines of code. All of them are combined in such a way that the entire program is like one function call. Okay. And then in your main method, which we dramatically call the end of the world, only then we're going to call this function. And so until we call this function, we're in this perfect world where the substitution model for procedural application applies. So we can very safely reason about our code. We can very safely refactor our code. We don't have like weird bugs. We still have some bugs, right? It's not bulletproof, but at least we can reason about programs with this substitution model for procedural application. Okay. The next couple of commits, they're sort of like steps to how it's done. Okay. So most of this stuff is done in libraries. Okay. So what we're going to do over here is we're going to write our own library. Okay. So it's just like over here, right? So it's just like another file over here. So it's like in a package functional programming library. And then over here, I just kept writing everything in this file. We're importing everything from this library and we're using using it at the bottom. Okay. So a function that does not contain any arguments is called a thunk. Okay. So this is a thunk that will produce an A. Ignore this plus, completely ignore. Okay. So when I'm going to call this function by giving it no arguments whatsoever, it is finally going to give me the A. Like in our example, the A is actually unit because it's just going to be like some sort of print line. Now, for convenience, we're going to take this thunk and we're going to wrap it into a data structure. And it's going to be called IO, which stands for input output, right? So it's for those things like, okay, like how do we actually send an email? Or how do we actually read something from the database? How do we print stuff out? How do we, read, user input in there? It's just a data structure that contains one of those thunks, right? And usually it's called unsafe run because until you run it, your entire application is safe, right? It means that it's within the substitution model. However, as soon as you run it, all bets are off, but you're not going to run it. And we're going to get to that point. Now, this is a companion object for this class. And if you're not familiar with Scala, companion object are ways to have sort of like static methods, right? So we can do io.delay without having an instance of io. Okay. And that's just a helper function to where we can give it an A. It will wrap this A into a thunk, and it will wrap this thunk into an IO. And there's a tiny trick over here. This is called a by name parameter in Scala, right? And you can think about it as if this was already a function, right? And so over here, we're just calling it like this, right? So this means that under no circumstances is this A evaluated, right? It's, if you give it a 5, this 5 only be evaluated at the very end of the day when somebody calls unsafe run, right? So over here, it's going to, this is just like syntactic sugar for what I've just shown you. The value of A is not known here. It's just being captured in the function. Okay, so this allows us to do like, to go over here. And whereas before we just had these curly braces, now we can just say io.delay. And in Scala, whenever a function has only one argument, you can replace, the paren, which would be like in any other language, right? You can replace them with curly braces. Okay, so this is a function call. Everything inside of these curlies is one thing, and therefore we're passing this one thing to this function delay. Remember, it's being passed by name, so this print line did not happen yet. Okay, so it goes in over here. It is being stored in a lambda. The lambda is being wrapped around in a data structure IO just for convenience. Okay, so what happens now is that we don't have this withdraw yet, right? But like what happens now is that already these two programs, like these two, well, technically like these two, right? Like print lines, like these print lines are just for you guys, okay, just to see, okay? But like as you can see, like this program is now equivalent to this program, right? You kind of see over here like the objects are different, but this is just a, this is not what this is about, right? Obviously, these are two different objects, right? But the program behaves exactly the same, right? Because what are those objects? Well, those objects are descriptions for running computations. Okay, so we can go over here, right, and write a little bit of code and say, okay, well, I'm just a description for some program. Okay, so, and as you can see, we just have two tuples, each with a description, 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 description. And there we go. This is it. Like, this is how this problem is solved. It's just that now you kind of have like other problems. It's like, okay, how do you work with these things? Okay. And this is how we're going to move on, because now we cannot do this pipe, right? Because now it's going to say, well, withdraw is not a member of this IO thingy, right? And this is how we're going to go to a function called map, which is going to do what pipe used to do, but for these like nested things, these wrap things, right? So map will know how to go like inside of this IO and convert this value sort of like without running it. It will describe how to run it, right? But like none of this stuff is going to run just yet, right? Which means when we're going to call map over here, it is going to produce just another IO, just another description. And same as with the immutable bank account, we're not doing anything with it, right? And therefore it will stay fine. Okay, let's see what is happening in the next commit. Let's check out v10. V10 now basically has this line, which is just a comment, right? But this is separation between the immutable part of the application, right? And I'm saying immutable, I mean like between the part where the substitution model for procedure application is not broken and the other part. Okay, in functional programming languages, you will never even have this thing. For example, in Haskell, right? In Haskell, the main method does not return unit; it returns IO of unit. Okay, and so you will construct all of your descriptions somehow, and you will just give it to the runtime, and it will run it. So your program, like 100% of your program, is within the substitution model. Okay. We didn't get there just yet. We're gonna have conversations about this in just a bit. This is where we let things blow up, right? So this is where we break the substitution model by actually calling unsafe run. This is now unsafe, right? And usually you would have like only one call to unsafe run, but over here we kind of like, for now at this stage, we have like what, like 6 programs, right? Because I wanted to show you that all of them behave exactly the same. Like as you can see, they all say producing one, producing one, producing one, producing one. Okay. Now where are actually our bank accounts, right? Because before we were printing out the bank accounts. Okay, and I believe this happens in V11. Okay, we're actually surrounding this with a print line, and now you see that all of these programs behave, all of them are identical. Okay, they first do a print line or producing one, and then they're actually giving you the mutable bank account. So I want to reiterate a little bit. So what we did is we had side effects, and we converted them into effects, pure effects, right? So this is also the reason why IO is sometimes called an effect type, right? But it's just a data structure, just a wrapper around the thunk. Okay, let's go back. Let's see what I did next. Okay, and by the way, we're gonna start moving like faster because we have 32 commits to go through, but we're already at 12. Yeah, so the next one is the map, because we somehow need to withdraw, right? Like how can we withdraw? Like the only way we can withdraw right now is by calling unsafe run, which we don't want to do because like we want to do it here somehow, and we cannot call unsafe run here because we want to be in the safe vault of the substitution model. Okay, so what we're going to do is we're going to define a helper method on IO, right? That will, in an immutable way, call unsafe run for us, right? But it's not going to call it, right? It's going to just create another IO that will call it once we run the entire application. Okay, so if we go over here, it's pretty much exactly what what we need to do. So unsafe run, for example, it would actually get the bank account, right? So the A is the bank account, right? Then we will apply the transformation, which is going to be the withdraw something, right? And that's how we're going to produce the result. Okay, so compare this with the immutable bank account, right? So if we go to the immutable bank account, okay, so something like a deposit, it's the same pattern, right? There's some parameter goes in, and then the first thing that we do is we're creating another data structure, right? Another mutable bank account. Same thing is happening over here. We have IO, we have a function, it has some parameter. The first thing that we're doing is we're creating another IO, okay? And thus everything that is happening here is not happening yet. It's just a description, right? Because remember, like this is just syntactic sugar for creating IO and, you know, giving it a thunk, okay? So all of this is inside of that, right? So this is just like a helper. This code does not run yet, okay? So we're just giving it a function, you know, we have an IO of A, we want an IO of B, so we give it a function how to go from A to B, okay? It creates an IO, it calls unsafe run to get, you know, it describes how to call unsafe run to get the A out, it sticks it into this function over here, right? This is how we get B out, and there we go, we have IO of B, okay? And so now, over here, what we can do is we can map, right? But as you can see, our programs are not affected, right? The programs are still the same. Why? Again, because this is just another IO, okay? And we're not touching this other IO, right? This is an IO of unit, but we're not doing anything with it, so it doesn't affect our program at all. It's exactly the same as what happened to our immutable bank account, right? So over here, you know, right? It just creates another immutable bank account, but we're not doing anything. We don't care about it. It's a new bank account, like whatever, okay? So let's see what happened in 13. This is an important one. This is what I was saying before. In a programming language like Haskell, this runtime that knows how to run this description is built into the language. In Scala, we don't have that. And in fact, this is one of the biggest reasons why I'm making this video, is because we have competing libraries that try to do that. What these libraries do is they create a trait, usually called like FPApp or something, right? So I put it like in the FP library. It looks like this. In fact, like there's a lot of like mechanical stuff that I would need to explain to you about how this works, but essentially it's just like a template class where you implement the run function, which, you know, you give it an IO of any, and all it will do is it will call unsafe run for you, okay? So essentially what happened over here is that I removed this like def, the whole thing now became an object, and I do like extends FPApp, okay? And now somewhere at the bottom, I'm gonna say, well, run is going to be this one delay, right? So we're giving it like one, right? So technically like this line is not correct anymore, because this is still like one description, okay? So we're giving this description to the runtime and it calls this one function, right? Like our entire application became this one function, right? Over here, this is our entire application, and the runtime simply runs it. I also put some green color around it, like this, okay? And this is why the whole thing looks green, okay? But now, like, imagine that this library is not, you know, it's just on our class path, right? We haven't written it, okay? And therefore, our entire program is purely functional. This is what it means to be purely functional, right? The substitution model is not broken anywhere. We can reason about it in a beautiful way. Okay, so it doesn't really matter how exactly this stuff works, because again, there's some mechanical things, like app is a very special trait which uses some delayed initialization techniques. So it needs to be like an abstract class. If it's a trait, you know, then it's not going to work, you know, but all of these things are like just, you know, some very specific Scala things. They have nothing to do with what this is all about, right? So it's just a template, we implement run, and it just calls unsafe run, right? So the unsafe code is not in your application. It's in that library. So you don't need to worry about it. Your program is 100% purely functional, which does not mean that you cannot have bugs, right? None of this stuff is bulletproof. Let's see what I did next, because I believe we're going to start talking about monads. This one is just like, usually you would have like a distinction between like your program, right? And like this part that actually does, you know, the extends app and, you know, and run, okay? So this whole thing now became an object, right? It kind of like ands over here, right? You can do like and program, right? And like it has a value, which is our, you know, one single IO delay, was like, this is like basically our program. And, you know, we're just doing like this one call over here. Like we don't even have this one call where we call unsafe run. The library does it for us, okay? But this is pretty much like the pattern, right? So you have like your main is that it's gonna look like this. Okay, this is just a refactor, okay? So the next one is the path to monads, right? Monads, really big word in functional programming. A monad is just a mechanism to chain these descriptions, right? So the same as before, we couldn't call pipe, we needed map. Now we're going to realize that map is not enough. We need a slightly bigger boat to compose these. Okay, so what we don't want is, we don't want to have like one IO, one description, and then the description to be gigantic. And the second one is that what we don't want is, we don't want to call unsafe run. Okay, even though it's within IO and everything is kind of like fine, we really don't want to have that, because this means that inside, like everything that is currently marked, like everything inside of these curly braces, within this, even though tiny piece, we cannot apply the substitution model. And we don't want that. In fact, some really advanced cases actually require you to do this, but we're not going to do any of this stuff over here. Okay, so one thing that you always hear about functional programming is that you can create like very, very small things and then combine them. This is the opposite, right? We have like one very, very big thing. So what we want to have is, we want to split these things into many like small IOs and find a way how to combine them, right? How to chain them, how to compose them. This is like the word that is usually used. Okay, we didn't check out 15. Okay, so let me see what I did there. So the first one, like, it's pretty much a refactoring, right? It's a refactoring to just explain, right? So like, this is like the old value now, and this is like the new value. Okay, so it's still an IO, still delay. It's exactly the same thing as before, right? Over here, right? But now we try to use, first of all, we have like these vals, right? Just to remind you that everything has a value. And then we try to remove unsafe run, right? And we successfully removed unsafe run. So instead of unsafe run, right? So instead of, for example, of this one, right? Like println, and we give it TE, which is a tuple of E's, and we're getting the first value out, and we're calling unsafe run. Instead, what we do is, we're getting the first value, sort of like pipe, remember? Like pipe, println. We know that pipe doesn't work, but we know that we have map. So we try and with map, and we successfully removed unsafe run. However, our program does not behave the same as it was before. So we see that map is somehow not enough, okay? Because what is happening over here is that E is some sort of IO, right? It's an IO mutable account, okay? When you call map, well, you're converting this IO into IO of unit. Okay, well, great. Now this underscore is IO, but you're not doing anything with it, right? So map calls unsafe run, but we need to call unsafe run again, right? To call this description, right? We need to call unsafe run, and we need to tell it that after it runs, it also needs to do the next thing, which is like this println, and then do the same thing with the next one, and then do the same thing with the next one. Okay, let me see if we're doing this already in the next one. Well, not like this, right? Like this. No, okay, we're not. Okay, so the first thing that we're doing is, we're going to try to chain them, right? To connect them with map. So I believe what I did was is I took like I believe these three. Yeah, so as you can see, T1 map println, right? And then I tried to like take these three out. I put them like before here, and I wanted to like experiment with it a little bit. Okay, so if we check it out, okay, so I commented it out. And I said, okay, so let's try to use map. Let's see if map is enough. And it looks like it's almost enough, right? So TE1 says, okay, producing one, and then immutable bank account because of this map println. Great, okay. Then we do map println these underscores. Great, this works. But then we do map TE2, and here we're lost again, right? Because like, remember, we cannot do this, right? Like we cannot do this, right? We're not allowed to call unsafe run, okay? So, and then we're kind of lost. We're in this description world again, right? So we're like over here again, override lazy val to string, which is a string, equals description, right? So we need to call like unsafe run again. Like this is the trick. We need to call unsafe run twice somehow. Okay, I'm pretty sure that the next one, the version 17, is just to explain the add expansion over here. So this println is basically, okay, the bank account comes in, and we do a println of the bank account, right? So as you can see, they're all the same. Okay, now, but they're not all the same, right? Because like println is something that is already happening, right? It gives you like a unit, right? But over here, like this is an IO of unit, right? And so we need to continue, right? Let's see. The version 18. So the first one is, okay, let's level the playing field. Let's make them all equal, okay? So we cannot make them all, like we can either go like down, right? So we can call like unsafe run, Okay, now they're all like sort of like executed, right? Print lines is executed and save run is executed, okay? But we actually want to go the other way around, okay? We actually want to delay the print lines, okay? So we check out 18, we're going to delay the print lines, okay? And now all we need to do is we need to create another combinator. Instead of map, we're going to call it flat map, okay? Because now what is happening is that we have IO of IO. So we need a map that will then flatten the IOs, right? How will it do this? Well, it will call and save run again, right? So if we go to V19, right, you're going to see that we're calling flat map now, right? So everything is IO here, right? And flat map does exactly what we need. And flat map looks exactly like map, right? See, the only difference is that like this thing is an IO, right? Before it was a B, which in our case was like a unit most of the time, but now this is an IO. And the implementation is almost the same, right? So first we're getting the A out, but then when we call the function, we don't get the B, we get the IO of B. And so we call and save run again. And this is how we get our B, okay? And so again, we went from IO of A to IO of B, but this time was a different function. And, you know, a hand-wavy way to explain monads is that monads is like that thing that has a flat map. Pedantically, there are also laws and stuff like this. I have an entire playlist about monads. If you want, you can check it out. Okay, but for now, a monad is something that has a flat map. Let's continue. It's like, I believe from here, everything is fast. 20 is the one that, okay, so I did a kind of like a big jump over here, okay? So now we can see how we use like flat map, flat map, flat map, flat map, flat map. Scala has a construct called for comprehensions, which allows us to basically maintain this code like almost as is, okay? It's just that these vowels will go away. These equal signs are going to look like this, okay? And over here, remember, this is going to be like delay print line, right? And this thing over here, right, it's going to have a 4. In Scala 2, there will be also a curly brace. In Scala 3, it's not required. And then over here, in Scala 2, it will be closing curly brace, and then yield, in our case, what we're yielding is a unit, right? Because this was an IO of unit, okay? In Scala 3, we don't need this curly brace, okay? So I'm going to do throw out what I just did and check out V20. And this is exactly what I just explained, okay? So instead of like doing it yourself, flat map, flat map, flat map, you have this for comprehension. Technically, it's not like precisely the same because these are nested flat maps. What we had before was like chained flat maps, okay? And this is something that has to do with this monadic laws, right? This is the associativity law. It says that they should be the same. Like whether you nest things or whether you chain things, it should behave exactly the same. That's also why it's very important to test laws when you create your own instances of monads, but usually you don't do this because usually libraries do this for you, okay? Now there's still some discrepancy, right? We still have like a map over here. Remember, we didn't remove it, but as you can see, it already works. Okay, so I believe the next steps are going to be to do, you know, flat map and then delay the print line and so on. So let me just check out V21. Yeah, so this is like the next step, right? So we're going to flat map, and then we're going to have a B, arrow to the right, IO delay, print line B. Okay, and the next one is going to be an introduction of our own console that is going to do this whole delaying for us, because what we want to do is we want to have add expansion, right? What we want to have is we want to have flat map and then our own, you know, I believe I call it FP console dot println, because over here we cannot use that expansion. The next one is going to be 22. Right, which has this, yeah, it's pretty much exactly what I said. And FP console is just a teeny tiny object. It has print line and read line, okay? Print line has a delayed, you know, by name parameter A, and all it does is IO delay the regular print line. So this is the regular Scala. This is the print line that we have been doing all along. It's just that I cannot do it like this because otherwise it would like refer to itself. So I needed to do like console.println. And the read line is pretty much exactly the same. It's like the opposite. It just delays, you know, the read line from the standard library. Therefore, it gives you an IO of string. Okay. And there we go. Okay. And the next one pretty much like rewrites, you know, the rest. And it also shows you that because we're dealing with descriptions, we can store a description in a val, you know, with these hyphens. And we have this for comprehension, which says, okay, we'll do hyphens first, you know, then take a bank account, flat map to print line, then do the hyphens now, do the blah, 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 blah. But now we also have like flat map inside of a for comprehension. So we don't really need this, right? So I'm going to rewrite one of them by hand. And then I'm going to check out the next commit, and it's going to do this for the other ones, right? So basically, we could say, okay, well, get the bank account from the E, which is a description of how to get a bank account, okay? And in the next step, just do FP console println b. Okay, because like this thing essentially is a flat map, right? So it's gonna look like this. It's literally the same code. As you can see, behaves exactly the same. Okay, so let me do this. Whoops, v24. I'm gonna check out v24. There you go. This is exactly what I just said. Okay, get the first bank account, print it out. Get the second bank account, print it out. Okay, right? It's exactly the same program, right? So this is like a huge for comprehension. And by the way, when you're dealing with real functional programming code bases, like very often you would see like these huge functional programming, this huge for comprehension. I really recommend you not to do this, right? Because now you're in the functional world. You can extract every little thing into its own val, into its own def. Please do this, okay? Let me see the next one. So basically we're going to, instead of having this program that does like all of these things, we're going to go back to the original program that we have written. Remember the one that starts with a bank account, like adds $20, withdraws like 5, I believe, right? It just says written in this functional style, okay? And I did this for the mutable and for the immutable one, okay? So now this is our program, okay? And as you can see, like at the end of the day, this program looks pretty much the same as it always looked like. It's just that now it's inside of the for comprehension, okay? So if we go to like check out v1, as you can see, it was, well, maybe not v1, hold on. Maybe like v3, maybe v4, yeah, like this one. See, it was like print stuff out, create this bank account was like 0, and then deposit 20, withdraw 5, and then another print, print out the balance and println 50. Okay, so this is now how it looks like in a functional world. Okay, println 50, create the mutable account was 0, deposit 20, withdraw 5, println the balance, and do it on the println. Okay, and in an immutable world, looks exactly the same. It's just that over here you don't even need to do these delays because everything is immutable anyway. Okay, so inside of a for comprehension you can also do equal sign like this and go like that. Okay, like this. Now in a mutable world you could do the same thing and you would actually not like most of the times you would not break anything, but there's a super subtle difference, and for like 100% purity's sake, you should not do this. And I'm going to show you why a couple of commits from now, maybe even in the next one. So what the next one shows you is that we're going to remove this thing and we're going to run our program still ourselves, right? By calling like unsafe run. And what we're going to do is we're going to show that over here, we're calculating the description, right? Remember, we're always calculating the description. During the calculation, we should not initialize any mutable state. Okay, we should also not mutate anything during the initialization. Okay, so over here, when this class is being created, there is some mutable state that is being created. This current balance is a var. Okay, so if we were to put a print line somewhere over here, in fact, let me check out v26. Okay, so it puts a print line over there. Okay, and now this demonstrates the substitution again. Okay, so I'm going to comment this out. I'm going to yang until the end. Okay. And I'm going to put it like, see, as you can see, like there's no delay here anymore. There's only like equal signs, okay? So if you have this program, right, notice that over here, we're not running it, okay? So if we do like unsafe run, now we're running it, okay? But we're not running it, right? We're just saying, okay, just give me the description. The thing is that like objects in Scala are lazy, which means that as long as like you don't touch them, like even though this is a val, it's not going to be evaluated. This is exactly why I'm accessing it. I'm forcing the evaluation, okay? But this is just a description, right? Like this is just IO of units, so nothing should happen. However, if you are not careful with the mutable state, even though you have IO, you're going to run into issues, right? Because again, this is a substitution model, right? So imagine that there is this val, and instead of using it over here, right, like this, right, if you do it like this, right, so sort of like the opposite of substitution, right? So instead of using the value, we're actually using the reference, right? So now, as you can see, we're sending rockets to space, even though we didn't even run the program yet. It's just that during the creation of the description, we accidentally sent rockets to space, okay, like this. Okay, so be careful, right? Like avoid mutable state like a plague. So the next one is going to be like, let's forget about bank accounts. Let's do a functional programming hello world. Okay, git checkout 27, and I believe it's actually in a different file. So this is the functional programming hello world. Okay, so it we need to switch to running it. We're going to run it only once, right? Like this main. Okay, so it just says, okay, what's your name? My name is Vlad. Hello, Vlad. Okay, so this is the functional programming hello world. This is how it looks like. First, we're calculating the description, right? So this is the IO of unit by using for comprehension, print line, read line, print line, and then we're giving this program to run. Okay, this is the functional programming hello world. Now, I believe the next one requires a lot of explanation. So this is the path to Tagless-Final. There's a technique called Tagless-Final. Originally, it was created to solve the so-called expression problem, right? It was basically how can we add behavior or add new data types to our program without recompiling the existing ones. Okay, this was the premise of the expression problem. It's called the expression problem because the original example was a data structure which represented like mathematical expressions, you know, like adding two things together, subtracting the things together, and so on. Now, in the Scala world, we really adopted this pattern. It's called Tagless-Final. I have an entire playlist about it. You might want to check it out. However, we applied it to a very small problem. Well, it was big for us, but we applied it to like a very narrow problem. Okay, we did not care about the solution to the expression problem. Well, kind of did, right? It's all related. Okay, so I already mentioned this problem, right? Scala is not a purely functional programming language. Therefore, this FPApp IO is not built into the standard library as it is in Haskell. And so we have competing libraries to provide these effect types. And the Scala community is very small. A lot of projects are being maintained by like one guy or like a very small group of people. There are always like occasional community contributions, but it's not something that you can like, you know, rely on as a company. And so what happened over time is that we kind of took Tagless-Final as a mechanism to abstract away which of these libraries we take. And therefore, it's sort of like defensive programming. If one of the libraries stops being maintained, we can very easily switch to another one, because the way it works is that we abstract everything that we need from these effect types, and only in the main method we say which of these effect types we need. This pattern kind of dominated the functional programming ecosystem within Scala for the last couple of years, and now it's slowly fading away. It's still debatable, it's still very negotiable, like which way is better to develop applications. In my opinion, it's just not worth the trouble. I've been using it for a couple of years, and I concluded that it's not worth the trouble. So it's much easier to use an IO type directly, and we're gonna get to this. Okay. So let me see what I did in the first one, right? So this one in 28. If you look at this over here, like what are we doing? Okay, so we are calculating the description of the of a program, but specifically for this program, like which parts of IO do we need, right? And it turns out, well, we need that part that knows how to print stuff. We need to have that part that knows how to read stuff. And we also need that part that does the flat map, right? Which is like the monad part. What we did is we created type classes, which is a pattern that now I'm realizing takes a little bit of time to explain. So let's run through the explanation real quick. Every program, well, not every program, like every program of any like relatively decent size requires two kinds of polymorphism. One is called parametric polymorphism. Think of something like a list. Parametric polymorphism means that your lists can have many shapes, but independently of which shape they will be in, they won't change their behavior, right? Think about list of strings, list of ints, list of dogs. No matter which of these lists you have, the method size on the list behaves exactly the same, right? This is called parametric polymorphism. Independent of which shape, the behavior is still the same. The other kind of polymorphism is called ad hoc polymorphism, and it works the opposite way, right? If the shape is different, then the behavior is different. Think of this typical, animal dog example, right? So you have animal, the animal can eat or something, and now you have a dog, which is a slightly different shape of an animal, right? And it can eat in a different way, right? Because the type is different, the shape of the type is different, it behaves differently. Now, functional programming languages, they don't have subtypes. And so the pattern that they use is called type classes. In functional programming languages like Haskell, this is built into the language. There's like a keyword type class. In Scala, we mimic type classes. We mimic them with implicits. In Scala 3, it's not very visible because we kind of like moved away from implicits, and we also gave like specific keywords for something like type classes, but also not directly. We still don't have a keyword for type class. And in Scala 3, syntactically, you won't even see the difference in usage, right? In the declaration, there will be, but in usage, you won't see it. Okay, so what the next thing is, what the next commit is explaining is that in an object-oriented way to look at things, I/O is a monad. However, in a functional programming way, I/O has a monad. Okay, so the next thing I'm going to show you requires a lot of like Scala mechanics. Okay, so at the bottom we have two traits, actually three traits, right? There's also one for the console. Actually, I jumped like too far. I think I wanted to jump to 28 first. So we have like the functor and we have the monad, and monad extends the functor. Okay, and basically like we, in a hand wavy way, we said, okay, monad's everything and it has a flat map. Okay, so this is how monad looks like. Well, it pretty much has a flat map, right? But there's no like I/O inside. Also, there's like no thing inside that you're going to call flat map on. And the way this works is that like whatever extends this trait is going to have flat map as an extension method. Okay, so we're working with like parametric types over here. Okay, so we're saying, okay, so there will be a monad for some type f, which is of a higher kind, right? So there will be something inside of this f, like f could be a list, f could be an option, but in our case, it's going to be I/O. Okay, and because of this, we're going to be able to call flat map. And so like the definition of map and flat map, it stayed exactly the same. It's just that instead of calling unsafe run, so instead of calling like this unsafe run, we're calling I/O.unsafe run. And I/O comes from this like extension thing, syntax, okay? And so effectively I/O becomes a simple data structure, okay? But there's a type class called monad somewhere, which extends a functor, which doesn't really matter. And over here, there is an instance of this type class. So given an instance of the type class, if it is in scope, the Scala compiler will actually inject it for us. There will be extension methods on I/O, which are like map and flat map, right? So I'm actually going to show you this. So if you look at V28, right? So the functional programming library file changed, right? Was everything that I just explained, but nothing else changed, right? So this is what I meant. Like syntactically, like on the usage side, you wouldn't even notice a difference. Right? So for example, over here, the full comprehension still works because it still looks like as if I/O simply had a method called flat map. Okay, so as a user, you don't even see whether type classes were used or whether subtype polymorphism was used. But on the declaration side, there is a little bit of like Scala mechanics. Okay, so what this allows us to do, which I haven't done yet, let me check out 29, but I actually don't want you to see this file yet. Okay, a functional programming library. Okay, so checking out 29, and in 29, we also have another type class for console, right? So it pretty much looks exactly like this object. It's just that the methods are abstract and it's not hard-coded to I/O, it's hard-coded to some f, right? And so the result is like an f of unit instead of I/O of unit. Here is f of b instead of I/O of b. This is kind of hard to explain. Like this is another instance, right? So now it's an instance of a different type class. It's an instance of FP console of I/O, okay? It's a very subtle thing, by the way. These instances, they need to hard code for which type, right? And this is how you can do composition, how you can favor composition over inheritance in Scala 3, right? Basically, you're saying, okay, this instance is going to have like exactly these things, okay? So basically, like this export thing is doing exactly this, right? Like what just happened is exactly the same code. Right? It's just that I didn't need to do that. I could just say import everything that is inside of this object, export everything. Okay, exactly the same code. Okay, so now that we have these pieces in scope, we can write our program in such a way that it doesn't depend on I/O, but it depends only on these pieces. And the trick is that these pieces are in a separate library, right? It's going to be the library that provides these type classes, okay? So in our main method, the program is now, like, there's no I/O inside, okay? If you look for I/O, there's no I/O in this file, okay? So this is going to be a program for some very abstract f, and assuming that there is an instance of the monad type class for this f, and there is an instance of the FP console type class for this f, which is going to be I/O, then somehow we're going to do something and we're going to produce an f of unit, right? And so the program stays exactly the same, well, because the methods in those type classes are called exactly the same, okay? But now there is no I/O inside. And therefore, at the very end over here, type inference help us out, but essentially the compiler inserts I/O over here. This is the only place where we mention I/O, and therefore we can switch between those libraries, assuming that we have some other libraries that bring in the instances of those type classes. Okay, and so what happened in Scala is that we had a library called monix, which was which had a first mover advantage. It came with, I believe it's like io.monix, I believe it's io.monix, eval task. I don't have it in the class path, but it would compile with like certain things. It would compile, okay? Then after this, we had a library called cats-effect, right? Would work exactly the same way, right? And all of these libraries, they come with like a similar looking trade thingy here, you know? And cats-effect is a little bit confusing because cats-effect has I/O, it has instances for the type classes for I/O, but cats-effect is also that library that defines those type classes, right? That monix implements, and that the next library that I'm going to introduce you to is also going to implement, okay? And the last one is called Zio, right? So this would be like Zio dot, I believe it's called I/O, or maybe it's called task. I don't remember. That's not the point. One other thing that this Tagless-Final technique provides is what is called tracking. In particular, in this case, we're tracking the effect type, so it's called effect tracking, okay? So before, when this was I/O, you couldn't kind of like know what the program is doing. What is it describing? It could be a description of sending rockets to space, or it could be a description of simply printing stuff out. You would only know this once, after you looked at the implementation. Now, in this case, the implementation is just a couple of lines, so it's not a big deal. But imagine if this was like a huge method, okay? With this, you kind of see what it has access to. You see, okay, like it's going to be some abstract app, but all it will be able to do is whatever the monad, allows it to do, and whatever the console allows it to do. So it kind of gives you like this, a little bit of a false confidence about your code. And in practice, it turned out not to be that valuable. And by the way, this is just my opinion, right? Because what happened in practice is that most of the time, all of your apps will require a monad and also a capability to throw or handle errors, right? In cats-effect, it's called monad throw. Okay, and so most of the times, like at least this effect tracking portion was not valuable enough to justify rewriting the code like this. And I actually show you a couple of examples a bit later. Okay, so let's actually move on. We're almost done, right? We're 29 and there are only 32. Okay, so I believe the next one shows just a couple of syntactic things over here. So if you notice, we're not actually using the M anywhere, right? But the compiler knows that it's there because of this using thing. Okay, and so this one we do use, and there's a way to save a couple of keystrokes, right? And the way this works is that by splitting these parameter lists. Okay, so if we check out v30, you're going to see that now that these parameter lists are split, in this one you can mention the type classes that you're not going to need to reference by name, but in this one you're actually going to require the names. Okay, and we also have another syntax called context bounds, where we basically can say, okay, well, f is not a monad, but f has a monad, right? And the way it works is that we have like a colon over here, and we do like a monad over here. And it's a little bit shorter because we don't need to mention this f. Okay, so if I remove this and I check out 31, and this is exactly how it looks like. Okay, so usually, like in most cases, you would see like, okay, it needs a monad, and you know, it needs an FP console, and so on and so on. However, like in this particular case, because we actually need the name, it's more convenient to do it like this. Okay, another way to do this would be to like remove this and to have like a val over here, FPC, and you would say, well, could you please summon the instance of the FP console for f. Can you please summon this? And summon is just a function in the Scala standard library, and it looks like this. I'm gonna call it find or something like this, right? So find some a, right? And it's going to be like a using of this a, like this, right? And it will return this a, right? How's it gonna do this? Well, like this. Okay, so this thing works exactly the same way, right? So I can put find over here, right? And it's going to work exactly the same thing, right? FPC is like FP console of f, right? So basically the compiler will inject this a and we'll just give it back. So if we go back to summon, if we jump in there, you're going to see that, let's see, I can't find it, but this is how it looks like. Okay, go back to my code. We're pretty much at the end. The very last commit is going to show how these libraries are actually used. Okay, so in the build file, I went over here and I added Zio and I added cats effect. Monix is not published yet. Zio interrupt for cats is not published yet. In fact, maybe it actually is published already. Let's actually check this right now, because like some of this stuff is very new, because I'm using like a cutting edge version of Scala, right? So it's like the latest Scala 3 version. Zio 2 just came out, and let's see. So Zio interrupt cats, like as you can see, this one just came out 3 days ago, and they recently switched to an epoch kind of like release. So you have like major minor patch over here, but over here you have like the first 2 stands for Zio 2 and the second 2 stands for cats effect 2, and we need 2.3 for Zio 2 and cats effect 3, which is not published yet, but I'm sure it will be in just a couple of days. This is also like one of those things that like Tagless-Final technically protects you from your effect library not being maintained anymore. However, you might also run into this situation where, you know, the interrupt library is not maintained like as fast, at least. Okay, it's not exactly the same thing, but you know, it's getting there. And now, like in the main method, I have like a couple of versions over here, right? So this is like our version. In Scala, you can define packages inside of other packages. Okay, so this is still our version, still looks exactly the same. Okay, and this is our main, you know, and stuff. This is the Zio version. You're going to see that it looks pretty much the same way, just that the import is different. The console is like somewhere else. The method is called slightly differently, you know, println, readline, blah, blah, blah. The main looks pretty much the same. It's just that we're extending that thing from that library instead of ours. This is the cats effect 3 version. You know, we import cats effect star. There's a slightly different way to obtain the console, but or however the, you know, saying goes, you know, println, readline, blah, 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 right? So this is now, it's kind of hard to read, but essentially it's IO unit. Slightly different trait, you know, named slightly differently, but behaves exactly the same, you know, IO app, simple. Now this is a mix, like this is a Tagless-Final approach, but we cannot inject like any other effect type because the libraries are not published yet. So the only effect type that we're going to inject is going to be still cats effect. Okay, so as you can see, we need like more imports. We need cats because it brings the monad type class. We need cats effect, which brings the console type class. We need the syntax so that we can do the dot flat map. And in the end of the day, the program looks pretty much the same, right? So yeah. These are all the versions. This entire repository is going to be available on GitHub, and you can check it out at your own pace. Let me finish this video by saying a couple of words. Now, which one should you choose? In Scala, we have basically either 3 options, right? Either monix, cats effect, or Zio, or you can go with Tagless-Final, and then at the end of the world, you can decide which of the effect types you're going to choose. Okay. Now, monix has the first mover advantage. It's been around since 2014, 15, maybe even 13. It's a very good library. In fact, we still use it at work. The issue with it is that the bus vector is very scary. Okay, it's maintained by a very small part of the Scala community. In fact, recently the main maintainer had some personal issues in his life, so it wasn't maintained for a couple of months, or maybe like even half a year. Luckily, he came back, so it's still alive. It's not dead or anything like this. Cats Effect is a battle-tested library, especially Cats Effect 2, because very recently Cats Effect 3 came out, and only the time will tell how it behaves. You cannot go wrong with Cats Effect 3. Zio is probably like the youngest one of them. However, the youngest also means a couple of years. Just a couple of weeks ago, Zio 2 came out, and again, only the time will tell how good it is. Zio is slightly different from the other two in how it handles errors, and also it has an optional way to do dependency injection differently, but you don't need to use it. Tagless-Final, it's kind of fading away, at least in my opinion, because in my opinion, it's not really worth it, because like the really big fear was that some of these libraries are going to die, not going to be maintained anymore. I'm betting on Zio. It doesn't look like it's going to disappear anytime soon. In the previous video that I made was for seasoned Scala developers, and over there I pretty much said that Zio is winning, but it's not like it was not an easy fight, and it's not an easy decision to make whether to use Zio or Cats Effect or Tagless-Final. However, I would still choose Zio because Tagless-Final to me personally is just not worth it. However, you are a beginner, and as a beginner, this decision is much easier. Zio is much easier to learn. It's more beginner friendly. Even if you just look at what we just did, the hello world, even just a hello world in Zio, which is over here, is the most pleasant one out of the three. Okay, so it's more pleasant than the Cats Effect because you have to obtain the console in some weird way. And it's more pleasant than Tagless-Final because you need like extra imports. You need to understand like type classes and all this relatively heavy Scala syntax and intrinsic details. But this is mostly just a personal preference. Like in the previous video, for example, I said that if you already have a big code base in Tagless-Final, you're not going to gain too much from rewriting it to a concrete effect type like Zio, for example. But if you're starting fresh, I would start with Zio. All right, now, as already mentioned, this repo is going to be on GitHub. And also, if this was too fast for you, I have videos about all of these things. I have a playlist about Tagless-Final. All of them are here on YouTube, free playlist. So I have a playlist about Tagless-Final. I have a playlist about Zio. I even have a series about Git. I have videos about, ZSH, where I use like all of these aliases. I have videos about all of these kinds of things, right? So don't forget to subscribe, even, hit the bell if you want to be annoyed by the notifications. And, if you stuck around for so long, you obviously liked the video, so please hit the like button. All right, I hope you enjoyed this video. I see you in the next one. And for now, as always, it's been Vlad from devinside.com. Don't forget to like this video if you did, subscribe if you're serious about improving the developer inside you. And if you have the means, consider supporting me on GitHub sponsors or Patreon, and sometimes even watch my videos before everyone else. And most importantly, take care.